Alright, so today I have this old GFI outlet. It had to be taken out because it's broken. You can see both buttons are pushed down. One is squished to the side a little. And I wanted to see what's inside of them because I've never seen what's inside before. So today I thought I'd share it with you. I'm going to take it apart. Get some screwdrivers. It's got little screws on the back, 4 little screws. I hope that gets it off. These are the terminals that go into the power from the panel. These ones are the outlets to protect other outlets with GFI. These I've heard called RCDs, ELCBs, all these other things, GFCI. What they basically do, for those who don't know, is that the power is escaping from the circuit. If anything's going through the ground or going into the ground or into a person or into water, the whole thing trips. The outlet will stop providing power. So how do they do that? Let's see. Well, that screw's kind of stuck. This one's rusted to hell because it was in a pool room. Mechanical room with all that chlorine, just everything. The terminals are rusted. The plastic is bleached, just not in good condition. Something must be wrong with the thread. It's probably rusted again. The other ones are coming right out, though. Well, I've stripped it. So it's going to have to be cut. Let me go get something to cut it open with. Okay, I'm back. I'm going to try to get the screw out some other way. Try prying it open with a screwdriver. Prying open the case. Like I was saying, this thing doesn't even work anymore with those buttons pushed down like that, so it's not like it's gonna hurt anything if I just bust it. Just tear open the case with these, maybe. I'm not trying to get this back together in a functioning unit. Already garbage and should have gone in the trash already, except for I want to do this. I'll show you guys, show myself. Well, that was a little abusive, but I think it'll open now. Okay, so I finally took it apart. The bad thing is that the actual mechanism that moves when it trips kind of flew apart. I had to pull on it a little and just flew apart. It had springs that went flying. So I don't have a good diagram of how that moves, but I do have a circuit diagram of basically what triggers it. We have, so the chip, so this part on the back is 2 current transformers. So you have the live and the neutral go through here, and they cancel each other out. They don't induce any current in this because they're both traveling in opposite directions. One's going in, one's going out. But now if you're having some kind of short circuit, water, someone's touching it, whatever, and it's getting shocked, the current will go through the live, escape the circuit, won't come back to the neutral, and that's going to cause a current to be induced in this. Now it goes to the chip, where it sends a signal, it has resistors, capacitors, things to stop it from being triggered by interference. It also sends a signal, the chip sends a signal up to this other one to try to induce a current to the neutral, to see if there's any problem with the ground. If we have a problem with the ground, we're going to cause current to flow if the ground touches a neutral in the outlet for some reason. So that will trip it too. Anyhow, this chip I looked up the circuit number, and it's designed specifically for these circuits. And they say it triggers an SCR. So what happens is, in normal operation, and everything's working normally, the current goes to the live, goes through, all these switches are closed when you push the reset button. Go to the outlet, go to any other outlets connected to the load screws. This switch is closed, and so it just keeps going through to those, and then any current that needs to go past each of these, the live sends an electrical current that goes through the solenoid. It goes from the solenoid, and it goes up to this switch, which is closed once the reset button is pushed. Some of it goes straight to neutral through this resistor and this capacitor. It's AC, it can go through a capacitor. Some goes to this diode. A 1 in 4007 diode is rated at, I think, 1000 volts and 1 amp. It's running with a lot less than that right now in one of these circuits, but it goes through that and goes to the chip, which gets full peak mains voltage. This metal oxide varistor, which is connected to neutral, and that's in case there's a short circuit. Not a short circuit, some kind of power surge. This protects from static, lightning, whatever else. And at first I thought I had something wrong with my circuit diagram because I didn't think the chip could take mains voltage, but it does. According to the datasheet, that's what it's meant to do. So it supplies it there, it's connected to neutral here. When it gets a signal from the current transformers, it basically sends a signal through this 470 ohm resistor to the gate of this SCR, silicon controlled rectifier. And that, like I said, this switch is connected to neutral with a capacitor too. It's also connected directly to neutral. So the gate's connected to neutral with the capacitor to prevent interference from tripping it. And the actual place where the current passes through, the main terminals, are connected to neutral. So this switch is closed. The SCR passes a strong current through the solenoid, which opens all these switches. You normally have this little piece right here is trapped underneath something when you push the reset button. All switches are held closed, but that gets untrapped. Whatever's blocking gets pushed out of the way by the solenoid. It has this little plunger in it that's designed to push it. So that gets just pushed right in like that. Comes out the other side. And that reaction causes everything all the switches to open. Once they're open, there's no more current flowing through the SCR or through the solenoid, which I think would burn out if they flowed current continuously. And after that, since this is open, the current flows up through this capacitor and resistor. It's only 47 ohms. Again, the capacitor has most of the impedance there. Goes through all this LED and these 4 resistors. They're all 3.6K. I might as well draw a little line on the capacitor there, the capacitor SCR, because it does have a gate that's connected to neutral, like I was saying. So here's from the gate. It's connected through this to the chip, but the end of its output goes to neutral directly. And the other thing that I need to correct right now is there's a 15,000 ohm resistor here, and so that little The little switch, that little strip of metal I was seeing in the first one goes from the test button, connects live from before the current transformer to neutral from after it, and redirects some current, and that trips it. And that's just to make sure the rest of the circuitry is working, to make sure it'll actually protect you from electrocution. So all of these, so once this switch is open, some of that current goes up through all these LEDs and just lights them, and that tells you it's been tripped. And now you can just push that reset button, all these switches will close, and it'll be back to normal. Current will go to the chip, keep it ready. It'll send a signal to the SCR whenever it needs it. All of these switches, which will open, fire the solenoid, open all of these, turn off the outlet, and protect you. Now, if we take this SCR, I was able to prove it's an SCR. It's a little thing that looks like a small signal transistor at the top. But if I take this ohm meter, take the two probes. This one is actually on the positive side of the SCR. I'm going to put this black probe, because the black probe, when it's in ohm mode, actually is where the negatively charged. Trying to keep everything in frame here. So if I connect this to the two output terminals, nothing happens. The meter stays shut off. But if I connect on here, and then on the gate, see the meter opens, where the current starts flowing actually. But if I connect it there and then move it, if I connect it, put the positive to the gate, or in this case it's a black terminal but it's carrying positive on my meter, and then move it back to the just the side terminals, it keeps conducting because of the gate was touched. Now it's an SCR, so it runs continuously. Until I move it, and then it goes back to not conducting. That's how this works. One thing I thought was kind of notable is that all of these strips of metal, and these in here, this is supposed to be able to pass 20 amps to its output, but all of these look pretty small, like 18 gauge wire or 16 gauge maybe. So I'm not sure how I was expecting that to work, but I guess they assume it's short enough pieces that whatever heat it makes will be able to dissipate. It's not like a long strip of it in a wall with insulation or something. It's not going to have a big voltage drop, and it's not going to burn anything down. Other thing I want to say is this could fail in lots of ways. It's not guaranteed to protect you against electrocution. And you could also be electrocuted by the live and the neutral at the same time, in which case no current's escaping, it's just going through like any other load through here, and then going back into the circuit. So this isn't a guarantee, but I'm sure it saved some life somewhere because of it. Well, it interrupts the shock. Also doesn't interrupt the current immediately, but as soon as it senses it, it tries. So I think it's a clever design, and a good thing to have in the places where it's required. And so if you've ever wondered how it works, that's how. I'll be leaving a link for the chip's data sheet. See you next time.